Optical dispersion in materials arises from a different index of refraction for different wavelengths of light. This is what separates all the colors in a rainbow and makes cut glass and gemstones sparkle with different colors. The index of refraction changes with wavelength because the dielectric permittivity changes with wavelength. Recall from Chapter 7 that the general trend of the dielectric permittivity is to decrease with frequency as the polarization processes become too slow for the high-frequency electric field. At the crossover, there is absorption of energy that appears as the imaginary part of the dielectric permittivity, which is the resistive or energy loss part. Because n equals the square root of the relative permittivity, n has very similar features. The narrow range for visible light is usually between resonances, where epsilon and therefore n actually increases with frequency. This is often depicted as a decrease in n with wavelength due to the inverse relationship of wavelength with frequency. The smoothly increasing n with frequency is called normal dispersion, where some materials have the opposite or more complex trend because optical light is closer to an absorption or resonance, which is then called anomalous dispersion. We can model the resonance effect and therefore the dispersion using the polarization model for an atom we used for dielectric materials. There, the z electrons of the atom are modeled as if their center of mass is held to the atom's nucleus like a spring, where the spring constant is described by a resonant frequency omega naught. We now consider the effect of an oscillating electric field described by an amplitude E naught and an angular frequency omega on the system. The electric force on the negative z electrons is minus Ze times the electric field, while the restoring force on the electrons is the displacement x times the spring constant. When these two forces don't cancel, their sum should give the acceleration times the mass of the z electrons from Newton's law. The z's cancel and mass brought over to give a very simple differential equation for x as a function of time. The solution to this differential equation shows that the electron's displacement in the atom will follow the electric field. The time dependence is the same as the electric field, but with an amplitude that depends on how close the frequency of the electric field omega is to the resonant frequency omega naught. When omega is near the resonance, the electron is greatly displaced and the atom is more polarized. The index of refraction n arises from the dielectric permittivity, which depends on the polarizability or the electric dipole moment, which is the charge times displacement per electric field. Substituting the displacement x we just derived gives the index of refraction as a function of frequency due to this resonance effect. In summary, the relationship between n and the frequency can be described using a resonant frequency model. Sometimes it is written with the local field correction. The equation can be converted from angular frequency to wavelength to give a reasonable working model for optical dispersion where the resonant frequency or wavelength is usually fit to experimental data. The relationship between index of refraction n and dielectric permittivity can be extended to electrical conductivity via the complex permittivity. The real part of the complex refractive index is the refractive index that we have been discussing previously. The imaginary part is the loss or attenuation of light due to absorption. The complex refractive index is simply the square root of the complex permittivity, which itself has real and imaginary parts, where the imaginary part is related to the frequency-dependent AC electrical conductivity. Thus, an electrical conductor which leads to dielectric loss also leads to optical loss through the attenuation term. The Kramers-Kronig relationship between the real and imaginary parts tells us that all of these properties are interconnected, so that there are limits to what can be engineered in a material. Any dielectric or optical absorption in a material, represented by a conductivity, means that there is a strong frequency dependence of the dielectric permittivity and index of refraction. Also vice versa. If there is a strong frequency dependence, there must be an absorption. As an example, let's consider a pure conductor. This means that the real part of the conductivity is sigma naught at low frequency, and the imaginary part is much smaller. The complex permittivity then has a large, frequency-dependent imaginary component. The complex index of refraction can be found from the square root of the complex relative permittivity, where the square root of minus j equals 1 over the square root of 2 times 1 minus j, according to the way electrical engineers work with complex numbers. We will write the factor with the square root as alpha to save some space. The reflectivity of light coming from air can be calculated using the Fresnel equations and the complex index of refraction. This gives 1 minus the real part of n, which is alpha, squared, plus the imaginary part, which is also alpha, squared, over 1 plus the real part squared plus the imaginary part squared. Multiplying out the denominator gives 1 plus 2 alpha plus alpha squared twice. The numerator is nearly the same thing, but with minus 2 alpha, which we will write as 1 minus 4 alpha over the denominator. Now remember, the conductivity is large, and if we stay at low frequency, then alpha is large. So we can approximate by only keeping the largest term, which is the alpha squared term, or 1 minus 2 over alpha. So for a good conductor, the reflectance is nearly 1, and the amount less than 1 depends on the DC conductivity and frequency. A mirror using silver, the highest conductivity metal, has a reflectivity of about 93% for visible light, which means 7% of the light is eventually absorbed. One could also use chromium, which doesn't tarnish like silver and naturally stays shiny, but the DC conductivity is about 8 times less, which means the reflectivity is only 80%, with 20% absorbed. Recall that the index of refraction gives the speed of the electromagnetic wave in the medium relative to the speed of light in a vacuum. Speed is omega divided by k, where the medium doesn't change with the frequency, but the wave vector k increases, or lambda decreases. Thus, we have the complex wave vector k, which has both a real and imaginary part. The imaginary part of k will turn into a real exponential decay when inserted into the electrical engineering equation for a light wave. The attenuation length is known as the skin depth, where the electric field only penetrates about a skin depth into the conductor. We found that the amplitude of the electric field, and therefore the current in a conductor, only penetrates the surface of a metal a distance of about a skin depth. This not only applies to light hitting a conductor like a metallic mirror, but also a metal conducting wire such as a copper wire. At low frequency DC current, the skin depth is very large and the current is uniform in the wire. However, as the frequency is increased, the oscillating field becomes more like a light wave and only penetrates the copper a distance limited by the skin depth. At very high frequencies, most of the electromagnetic wave is actually traveling outside the wire in a dielectric medium surrounding it. This is why coaxial cable or Ethernet wire is sensitive to surface damage and damage to the dielectric insulation around the wire, and making it thicker doesn't much help. The coaxial cable is specifically designed to transmit the electric and magnetic fields in the dielectric insulator around the central wire. Ethernet uses twisted pairs to contain the electric and magnetic fields to prevent crosstalk, but used for shorter distances. For very long distances and high frequencies nearing that of light, dielectric optical fiber is better than copper wire.